Okay, so let me start by thanking the organizer for inviting me and also thanking the developers and maintainers of open source abstract domain libraries and static analysis tools. So abstract interpretation is a mature research field with many, many years of research and development, solid theoretical results, strong practical results. There are maturity indicators. Maybe the most important ones are industrialization and commercialization of abstract interpretation tools. We have libraries and frameworks, so it is quite easy to extend, combine, and compare. Compare abstract interpretation tools. And we have in-conference artifacts, competition, repeatability evaluations. So basically, we can say that we basically know what we have to do in order to have things right, and we can tell when things are going wrong, this maturity. And so in this talk, I plan to questioning against the last part of the sentence. So can we easily tell when things are going wrong? And the talk is about the lesson that I learned while investigating a specific abstract interpretation tool crash. And I think that the lesson is not really too specific. It can be of general interest. So I will focus on tools that are extensible, meaning that they have an abstract interpretation engine for the fixed point computation and a pluggable abstract domain so you can change and see what happens. And open source because I want to see what they are doing. And most of it is based on code review, human code review, okay? So brief story behind the crash. I'm implementing the PPL library together with students, and I implement several versions of convex polyhedra with different characteristics with efficiency and so on. I need to test it. So I test it using abstract interpretation engines. So first test with Pagai, they look at okay, and other tests with ICOS or ECOS, I don't know the right pronunciation. It seemed okay, and then I changed the domain using the fpoly, which is a variant of the polyhedra domain with Cartesian factoring, and segmentation fault, okay? So you wear the hat of the software developer, and you look who is to blame. And in this case, it turned out that was a precondition failure when the abstract interpretation engine, ICOS, was calling the widening operator in PPLite. So if I was to adopt the blame culture, I should stop here. It's not my fault, it's their fault, and that's it, no talk, whatever. But it is not really nice to adopt this blame culture. So no blame culture. Let's ask a few questions as abstract interpretation designers. Why is there such a precondition? Why is violation gotten noticed before? Which is the best approach to avoid this problem? These are the questions. So widening specification, the first one is the classical one from POP 76 paper by Couzeau and Couzeau, also repeated in PLIB 92 paper, the one about comparing the widening narrow approach, etc., etc. And here it is, and here I have highlighted the point of view of the abstract domain designer and the abstract interpretation engine designer. So from the abstract domain designer, we see the widening needs to be an upper bound operator. There is also a termination condition, but it is not something that related to this talk, so I will skip it. So it has to be an upper bound operator. And this is written in blue because having this upper bound is going to provide safety, okay? And in the abstract interpretation engine, since the widening is already safe by itself, let's say, we can be more risky, so we can just replace the joins with the widening and nothing else. Risky is in red, but it should be clear. Red does not mean unsafe, just a little bit risky. If someone else does the right thing, it is okay, right? So widening is meant to replace join. But in the PLIB 92 paper, there was also footnote 6. And footnote 6... Footnote 6 was providing a different specification for widenings, which is risky, or riskier, let's say. So in this case, it is said that the widening assumes that the second argument includes the first one. And in order for this precondition to hold, the absent interpretation engine cannot really just apply the widening, but before widening, she has to compute the join. So in this case, widening is meant to be used in addition to join rather than to replace join. And this is fine too. So what about the implementation of abstract domain in the open source world? I am focusing on numerical domains. So APRON, ELINA, PPL, PPL Lite, VPL, these are all libraries on numerical domains, but also domains that are embedded into abstract interpretation tools like Framassi, Goblin, Jantom, ICOS, Seahorn, etc. The reasoning extends to non-numeric domains, for instance, the domain of finite automata, which is implemented into GoLisa. So we take the interval widening, for example, and we see that in APRON, the interval widening is implemented according to the classical POP 76 specification. But in PPL, it is implemented according to the footnote 6 alternative implementation. It is the risky one with the precondition. Okay? If you go to convex polyhedra and consider the standard widening, you see that no library is implementing the classical specification. None of those I have checked. Even though the specification in Couzeau, Olbach 78 and Olbach 79 are safe. Okay? All the libraries adopt the footnote 6 implementation, the risky one. And if you go for domains that do not have infinite ascending chains, nonetheless, they need to implement a dummy widening in order to be generic. And you can see in Framassi, the signed domain implements the classical specification, and still in Framassi, the generic lattice set domain implements the alternative widening specification. And this looks strange because we are in Framassi. We are supposed to choose one widening specification, not two. Okay? So we can classify implementation of widenings. Here are some classification depending on the domain and the implementation, because it may differ. The safe implementation on the left, the risk implementation on the right, and that's it. And there are other domains, of course. For instance, Logozzo can place here on the blue column or the red column the widening of pentagons, let's say, and whatever. Besides classifying the widening implementation, we can classify abstract implementation engines. And here we have things reverted. So we have safe engines. These are those that compute both the join and the widening. So those are meant for the alternative widening specification, footnote 6 in PLIP 92. And there are risky abstract interpretation engines, those that only compute the widening without joins. And these are meant to be used with the classical widening specification, POP 76. And you can see some of them. And once again, maybe Antoine or Logozzo, Antoine Minet, can place their tool on the left or on the right. Okay? So we have a binary classification for the widening, a binary classification for the engine, and we have a matrix of 4 cells, and we can place our combinations. And I will use Pagaille for any safe engine, ICOS for any risky engine, the octagons for any domain with a safe widening, polyhedra for any domain with a risky widening. But these are just representative. So, first quadrant, safe engine with risky widening, it's fine. Pagaille and polyhedra is fine, it is safe. And that's it. Okay? Second quadrant, safe engine and safe widening, fine. You are both your belt and suspenders, so you are safe. Okay? A little bit uncomfortable, maybe, but you are safe. Consist, you may lose a bit of efficiency. Why? Because you are computing joins before widening, and these joins are completely useless. That's it. Third quadrant, risky engine, like ICOS, and safe widening, like octagons. Still fine. This is the POP 76 setting. And that's it. Safe. It is also efficient. No useless joins that are computed. And it can be more precise on some domains. Why? Because some domains are not lattices. They don't have a least upper bound, for instance, parallelotopes. So when they compute the joint, they need to choose among several different possible incomparable upper bounds, and a wrong choice, a poor choice, can lead to precision losses. So if you split the joint and the widening into separate places, it is less likely that you will perform a sensible choice. So keeping them together, it is more likely that you preserve precision. And this is discussed in papers by Amato, Scozzari, and another paper on non-lattice domain by Gange, Nava, Schachte, Sondergaard, and Stucky. Okay, safe widening can also be as efficient as risky widening. One can think, one get the impression that risky widening, they do not have to compute the joints, so they are more efficient. But this is just an impression, because they do not compute the joint, they delegate the joint to someone else, so the overhead is still there. You are just wiping, hiding the dust under the carpet, right? On the other hand, safe widening, when they combine joint and widening, they can trigger optimization. For instance, for standard polyhedra, if you compute the joint, you compute the convex polyhedral hull, and you do a lot of work to find new constraint slopes. But the standard widening by Couzeau and Dolbach has as one of its main characteristics that it never considers new slopes. It can only keep the old ones. So you are doing a lot of work uselessly. You can replace the convex polyhedral hull with the constraint hull and obtain the same precision. And you can even have ad hoc implementations. Fourth combination, risky absolute utilization engine and risky widening. Well, this is the one leading to explosion. It is unsafe. Pros, known, it is unsafe. Cons, it is unsafe. Things can go wrong. Things can go wrong despite the fact that this precondition was recorded several times in the literature. Besides footnote 6 in PLIB 92, we have a full-blown example in the SAS 2003 paper by Bagnara here, Ricci, and myself. We have a couple of quotations from old works warning people, hey, warning, we have a precondition. And another couple of footnotes in another paper by Patrick, too many footnotes. And things are going wrong despite the fact that most software libraries are provided with a good documentation. They write the requirement. So here we have the PPL documentation, VPL documentation, and the PROM documentation. They all say the inclusion needs to be satisfied. And things are going wrong despite the fact that software libraries sometimes assert those preconditions, but these assertions are usually executed when in debugging mode, and when people does experiment with apps interpretation tool, they do not use debugging mode because it is inefficient. Side note on the verified polyhedral hybrid. This would have been a perfect fit for the verified polyhedral library. David. How it works, the verified polyhedral library, they do the computation, they produce a certificate, and then they have an engine to check the certificate for correctness. But I don't know why they have decided that the widening was the one and only operation not needing a certificate, so they are not able to detect these kind of errors. I don't know why. Monio will tell me with a coffee. And things are going wrong despite the fact that I'm not the first one testing an unsafe combination. Seahorn is an unsafe absent interpretation engine. It shares the same fixed point engine as ICOS. DAISY too. And they have provided artifacts for at least 4 conferences: SAIS 2013, POP 17, CAF 18, and PLDI 2020. And no one ever reported a problem. So why? I don't know. Well, let's ask ourselves, things can go wrong. Do things really go wrong? Short answer, I don't know. It's undefined behavior, whatever can happen. That's it. I only have conjectures. That should be clear, just conjectures. It was not my goal to find the smoking gun. No blame culture. Okay, my conjectures are that no assertion checking means fewer crashes. Delaying the widening for a few iterations means problem mitigation, and also widening is not monotonic. So you might happen to be incorrect, so more precise, but this precision is not correct in this iteration. But then, since the widening is not monotonic, you can lose precision in the next iteration and regain safety. But regaining safety by chance. You are lucky. So our question was, can we easily tell when things are going wrong? The answer maybe is no, not always. So this is the summary. We have 4 kinds of combination. 3 of them are safe. 1 of them is unsafe, potentially. What is the lesson learned, in my opinion, and the recommendation? Okay? We should fix that it does not mean correct. It means choose the right one. Fix to the classical widening specification, POP 76. Why? For all that I said before. Because it is safe and it is correct, efficient, and precise. So the message for abstract domain implementers, you should implement the blue arrow, make your widening from risky to safe, and we solve all correctness issue. And for the abstract interpretation engine designer, implement the red arrow, make your engine from safe to risky. This way you gain a little bit of efficiency and you can be more precise on non-lattice domains. So this is the suggestion. And here I conclude. We have different widening specifications going around, and they can cause confusion. Confusion can lead to crashes or more subtle hidden issues. My suggestion is to fix the specification and choose the POP 76 specification, the good old one. It has several good properties. It is the default one taught in abstract interpretation courses and tutorials. It avoids all safety issues. It can be more precise for some domains, and it can be as efficient as, or even more efficient than, the alternative one. Thank you very much. No. 76 was not a Popol? That's... Stick to 76. 77.
So, this time is me. The question about, so can you go back to the slide before? So I don't agree. So I think this only applies to numerical domains, numerical analysis. So if I take my termination analysis, for instance, this doesn't apply. So in my case, I actually had to, because it would be not safe. It would give you the wrong results. Because in my case, I had to, well, first of all, I didn't have, I had to do the join, because if I didn't do the join, then my widening would be eventually producing an unsound result. So in that case, I couldn't do just the fix, yeah?
I mean, when you implement the blue arrow, it means that you make your widening from risky to safe. That is, you implement the join inside the widening.
Yes.
So it is going to be safe.
Yes, but then I...
Unless you have found an error in the POP paper by Couso.
No. But then I cannot have... well, the problem is that I had a difference between the computational and the approximation order, in my case. So the requirement of an increasing function was only, in my case, with respect to the computational order, not the approximation order. So, yeah. If you have a distinction, I'm not sure it works. I mean, yeah, you maybe have to extend your table. Yeah, so then in my case, I had a distinction between those, and then I don't know where I place myself.
Let me say, I am assuming that the abstract interpretation tool is one of the classical one built in this way. So I know that there are even other specifications for widenings, but they are almost never used in the tools that are available.
No. I mean, it is the classic.
The one they have looked at, I mean.
Yeah. But so I think the difference is between the approximation and computational order, that here, I guess, are the same. And what happens if they are not? Then how do you extend the table, basically? Yeah.
I will think about it.
Okay.
Any other question? Yeah.
You mentioned apron, for example, apron in English, apron, apron in French. And in the polyhedra, there are also overflows that are not caught. And have you noticed that?
In the domain of polyhedra, when they implement it, they are not using arbitrary precision integers. I think they are using
even the join is wrong, or the addition, for example, can be wrong and things like that. So,
is that true, really? I
is
mean, they assume the real semantics and not the mathematical semantics. Okay, that's okay.
Yeah, but also they don't check for any overflow or things like that. And so that we don't have many examples. I think we don't have any example at all, but we know that it might be wrong.
I know that New Polka can be configured to compute with arbitrary precision integers, so they don't have overflows. I don't know if the default implementation has integers, machine integers, or floating point. I don't think so.
I think I am still looking for a floating point computation that give an incorrect result in polyhedra. I think since Alvax we know it's possible, but we have never found any example of program which is wrong because of that, and without assuming overflow. If you have overflow, it's even worse. But if you have one example, that would be useful to me.
Okay, so thank you, Enea.